In this video, we're still looking at solving trigonometric equations. So that's equations with trigonometric functions in them. And this is the fifth video in this series that is on solving equations involving trigonometric functions. They've been getting slightly harder each time, slightly more complicated. This one's not really much more complicated than the previous couple, it's just a little different. So let's take a look. So you can see our problem is to solve the equation cos 2 theta plus cos theta equals 0. So it's difficult when you have different amounts of theta inside the cos. You can't just combine it. If it was cos theta plus cos theta, that's just 2 cos theta, and then that equals 0, and then that's quite easy. But that's not what we have. So we want to try and change this to make it into a quadratic equation in terms of cos, like we did in our previous video. And then we can solve it the way we'd solve a quadratic equation. So let's note that I'm going to put up over in this box on the right, I'm going to recall some useful information and put some other useful things. So I'm going to start with this, that cos 2 theta equals cos squared theta minus sine squared theta. Now this comes from the identity that tells us when we have cos of x plus y, there's an identity that tells us what that is in terms of coses and sines. So if x and y were the same, so we have cos of theta plus theta, then if we use that identity, we'd get that it equals cos squared theta minus sine squared theta. So again, this comes from one of our sum angle formulas, which we've seen in previous videos, and which it's a good thing to remember or to have to hand so that you can use them for problems like this. So cos 2 theta is cos squared theta minus sine squared theta. We don't want to introduce sine squareds into the problem because that just makes things more complicated. We just want to stick with coses. So let's get rid of that sine squared in here. We can rewrite it as 1 minus cos squared because sine squared plus cos squared equals 1. We've done this several times in these videos. Always remember that cos squared plus sine squared is 1, so you can always change a sine squared to a 1 minus cos squared and vice versa. So get rid of these brackets, we get cos squared, a minus 1, plus cos squared, because a minus will cancel out. So we'll get 2 cos squared theta minus 1. So I'm going to straight away substitute this into the equation. So instead of cos 2 theta, I'm going to write 2 cos squared theta, and I'm going to have to put the minus 1 in as well, but I'll put the cos theta in first, then I'll put the minus 1 at the end, and that equals 0. So I've taken the equation we're given, and I've used this reasoning on the right-hand side to substitute that cos 2 theta is 2 cos squared theta minus 1. I've rearranged the order a little bit because now it looks more like a quadratic equation. We've got a squared term, a order 1 term, and then a constant term equals 0. So now we do what we did in a previous problem, in a previous video, and we say u equals cos theta, because then the equation becomes 2u squared plus u minus 1. So I've changed the cos squared to a u squared and the cos theta to a u, and this is what I've got. And we can factorize this quite easily to get 2u minus 1 times u plus 1 equals 0. And from this we read off our solutions, u equals 1/2 or u equals minus 1. So there are videos on how to factorize quadratic equations in the algebra set of videos, so I'm not going to go through that here. But if you're unsure on that, just go and watch those videos. So we've got our solutions for u, but we're trying to solve for theta here. So u is equal to cos theta. So we have cos theta equals 1/2 or cos theta equals minus 1. So great. Now let's take this first solution. This is a solution, but we're not given any range here. We're not told that theta has to be between, 0 to 360 or anything like that. So we have to give every possible solution. So there's going to be an infinite number. We just have to find what they are exactly. So we know that if cos theta equals 1/2, then theta equals 60 degrees is a solution. Now we know this either from putting it into our calculator, we'll do inverse cos of 1/2, or we use our exact triangles. This is an angle, 60 is an angle in our exact triangles, and 1 and 2 are sides in that triangle, so you can get that cos 60 is 1/2, so this is definitely a solution. And as soon as we know we have a solution and we don't have any range for the solutions, we know that we can add 360, any multiple of 360, any amount. So one amount of 360, two amounts, three amounts, or minus one amount, minus two amounts, and we'll get another solution. So we do that straight away. We say our solutions are 60 degrees plus 360 times k degrees. But are there any more solutions in that principal range from 0 to 360? That's the question. So if you imagine, if you look at this graph, if there was a line cutting the y-axis at 1/2, because remember we're trying to find values of x that give us cos x, or values of theta that give us cos theta 1/2. Well, if we drew a line, it'd cut the graph about here at this red dot. So that's our 60, but it would also cut it over here. There's another solution. Now the graph is symmetrical. We've seen this before. So this red dot is 60. It's 60 above 0. Then this red dot must be 60 below 360. So it's 300. So hopefully you can see by symmetry that if that first red dot is 60, the other one must be 300. You can also think about it that 60 is 120 less than 180. So the second red dot must be 120 above 180, and that would make it 300. So another solution or set of solutions is 300 degrees, again, plus 360 times k, where k is any integer. So we've got, straight away, two sets of infinite size of solutions. So lots of solutions, but that's only for the first solution to our quadratic equation. What about this other one? Cos theta equals minus 1. Well, this is actually easier because over the principal range, we can see we only get minus 1 at one very specific point. It's at this trough here at 180. So we go down to minus 1 at 180, and then we come back up to 1 at 360. So the only solution for minus 1 is 180 in this principal range, and then we again can add any amount of 360 to it. And we'll keep getting to another trough down at minus 1 if we go up by 360 or down by 360. If you imagine this graph was extended and this wave was going on forever. So these are all our solutions. So we have three different infinite sets of solutions. And remember, you always have to specify what k is. So k is an integer, which is a shorthand way of saying that is that k is in z. This symbol in between the k and the z here means is contained within, and then z with a double bar means the set of integers. So k is in the set of integers. And that is our final answer.